All right. So this is back to chapter 6. Back to chapter 6, and now we're talking about our third and final, really, topic in this unit, which is vectors. Vectors are going to take us, I would say, at least 2 days. We might have to add a third in there. I kind of want to see how it goes with our block scheduling. Our target today says, I can sketch and perform operations with vectors. So today is all about the basics of vectors. You have to hang on with me through some of the notation. That's why I gave you a handout, was to make it less painful. But you need to hang on with me through that. And then hopefully by the end of class, we'll start to get to the like, okay, I see what these look like. I can start to see what they are. Friday is going to be all about applications. So then we're going to see the vectors, and vectors are usually used to describe force. So something like, okay, you're pulling a sled behind you, right? At what angle is the rope of the sled and how hard are you pulling it? Says how it's going to travel. You're playing tug of war with your dog and you're both exerting force on that little rope. What's the resultant force? What actually happens to that rope that you're tugging on? So that's what vectors are usually used to describe. Today, again, is just going to be about trying to get the background. So first we have to get through the notation. Then we want to get to what they look like, and hopefully be really well set up for Friday when we'll get into the applications. All right. So vectors are cool. They're something that I remember doing in physics in high school. And I love them because I was using the math to do something that I could really picture what was happening, which I remember enjoying. So there we go. All right, ready? So on your sheet here, you have magnitude. Magnitude is, in our graph form, a fancy word for the length, okay? When we get to application form, magnitude is going to be like, how hard am I pulling against my dog? I don't have a dog right now, but I play tug of war with my neighbor's dog because I love her. So how hard am I pulling? That's going to be the magnitude. When we graph it, though, the magnitude looks like the length. All right, the next word is scalar. Scalar is a quantity with magnitude and no direction. In normal words, how we usually think of scalar is a constant. That's what we usually think of when we think of a scalar. So you use scalars a lot. We just don't usually call them that. 4x, 4 is a scalar. You're multiplying by a number. So then we have what our topic is actually about today, which is a vector. And a vector is a quantity with both magnitude and direction. Ready for my audio visual?
Hey. I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah!
All right, how could I not pull that up when Despicable Me tells the definition for us? If you haven't, has everyone seen that movie? Okay. If anyone online hasn't, you're missing out and you should watch it. All right. So vector, direction and magnitude. So then when we talk about magnitude of a vector, we are talking about the length of a vector And what you want to write down, because you'll see this notation kind of over and over, is our symbol that we use for magnitude of a vector. It looks like a double absolute value. All right, and I think it sounds a little bit scary, but here's what we're describing. We have an axis or no axis if we're, doing tug of war, but typically we want to try to put these on an axis so that we can do the math that we need to do with them. So if we have an axis, a vector will just look like a ray, right? Because it'll have an arrow. It'll have a direction arrow because it matters which way it's going, but it won't look like anything scary. It'll just look like a ray. When we talk about the magnitude of it, we're talking about, here's our magnitude. The length of that line is the magnitude of the vector. All right. So far, so good. We're moving on to vectors in the rectangular system. All right, vectors in the rectangular system. This is where it starts to look pretty funky. So you'll be okay. I promise you will be okay. Hopefully by the end of class today, but if not by the end of class today, definitely next class. All right, so now we need to talk about how do we specifically identify vectors in the rectangular system, the regular system. So we have this notation that looks weird. And what you speak is even weirder, but I love it. I hat and J hat. Don't they look like I and J with a hat on? Yeah, well, that is actually what they're called. I hat and J hat. All right, so I and J, you put a little arrow triangle on top. Here's what they're describing. They are describing X and Y in terms of vectors. Okay, that's really all they are. If you notice, I is the unit vector. It's the direction in the horizontal way. So you're going to think of I as your X. Your X that you're used to, you're going to think of it when you think of your I. And then J is going to be the vertical. J is going to be the Y component. All right. Why did they give them different names? To be honest with you, I'm not actually sure. But I and J instead of X and Y. Great news, they're still alphabetical. So just like X follows Y, I follows J if you get them mixed up. All right. So when we write vectors, we will actually write them with their I and their J, which will show you the X and the Y. So you have most of this already written out for you on your notes there. Here's what it says. A position vector V, I want to see what you're looking at, which starts at 0, 0 and ends at AB, can be represented as, here's what you're writing down. All right, vector V is AI plus BJ. Now they have arrows over them. You're supposed to write an arrow over it to show that it's a vector. When you get to physics, you can worry about that. I'm not going to write an arrow every time I write a V, okay? So you can mentally prepare for that. If you're in physics, good job. All right, so we are going to write our vectors in that general form where A is the horizontal component and B is the vertical component. And you should be able to tell that because A is matched up with the I and B is matched up with the J. Okay. All right, to draw yourself a picture. All right, in that space I gave you, draw yourself that picture. This picture is going to break down for you the pieces of the vector. So we have in blue is our vector V. All right, our vector V, I'm using the notation we just wrote down, which is AI plus BJ. Our vector is going from 0, 0 to some point that we're calling AB. So this is just to show you that when you think about a vector and you see the two pieces, the I piece and the J piece, you're just looking at really like the pieces of that triangle. How far over did it go? How far up did it go or down? That's what you're going to see with your vector. And again, we could label, if we were labeling, you know, the distance of that blue vector, that distance would still be that magnitude, would be the distance on that line. All right, so that looks weird. So let's put some numbers in it and draw, you know, right next to that drawing, let's give yourself a drawing with numbers. All right, here you go. Write down for yourself so that you have an example of, hey, okay, this isn't as scary as it sounds. Write down V equals negative 3I plus 4J. All right, to graph that vector, to draw that vector, all I have to do is count over, okay, negative 3 in the I direction, 4 in the J direction, and there's my vector. So this is making me think of parametric, how we had separate equations for X and Y, right, when we did parametric. Here's your part that's X, here's your part that's Y. That's how it's describing it with the I and the J. So that's not scary, right? No, that's not, no, it's not scary. I'm telling you, it's not scary. So you have this little ray that has an arrow on the end. We use the arrow to show what direction it's going in. If I want to go and I want to find the magnitude of this, let's see if I'm getting ahead of myself. Let's talk about it. If I want to find the magnitude of this vector, I hope you can see from the picture, all you need to do is Pythagorean theorem, right? So if this is negative 3 and this is 4, then the magnitude of V, we just do Pythagorean theorem. So we can do, the formula is square root of a squared plus b squared. You don't really need to think of it as a formula. You can just think of it as Pythagorean theorem. And you probably already know the answer. I like to think you do. So the magnitude of that vector is 5. So again, trying to get used to the fact that it has the two pieces. What do the two pieces do? They describe the X and the Y. How do I find the magnitude? It's just going to come down to Pythagorean theorem. Why do I care? Because if I know the direction that I'm going in, I can find that magnitude. I can say, how hard is that being pulled if I actually know where it went, which is kind of cool. All right, let's keep going. We're getting the basics down. So say I want to write a vector that doesn't start at 0, 0. That's this example. So go ahead and write down your 2 points, point 1 and point 2.
They're already written down.
Oh, they are. Nice. Thank you. All right, so draw yourself a little axis, because I'm going to cheat and pull one onto my screen so I don't have to draw it. If you had one of those cool stamps like people have. You know, those graph stamps?
I don't know. I didn't realize those were.
Oh, they're so cool. All right, so you already have the points down. So what do I do if I have 2 points and I want to write the vector? Again, I think it sounds scary. But all you need to do is plot the points and you will be able to come up with this vector. Okay? If you were to actually go to your book for this section and look this up, it would have what looks like a weird formula, okay? You don't need that. You need to use your brain and a graph, and you can come up with the vector. Ready? Point 1, 2, -5. Point 2, -6, 6. All right, it matters that they're 1 and 2 because that shows me the direction my vector is going in. What did we just say about a vector? We said that it had an I and a J component. So I'm going to start writing my vector with an I and a J. And now instead of using a formula, I'm going to use my graph. And I'm going to look and I'm going to say, hey, how far did it go over? Because that's my I, right? If it went from 2 to -6, well, it went -8 over. So I'm going to put -8 with my I. And how far did it go up? If I went from -5 to 6, it went 11. So 11 would be my J. This vector equation describes that line. Now I got a really good question first period. Somebody said, well, wait a second, if you go backwards, if you take this vector and you graph it from 0, it's not actually in the same spot, right? And what you're gonna see as we do applications is that we do a graph so that we can do the math to it. It doesn't actually matter what point it starts at and ends at. So we end up, it's called a unit vector. We end up putting everything so that it starts at 0 so we can do the math behind them. Because what we more care about is what direction is it going in, that we'll be able to see the angle, and what's the length of that vector that we can find with Pythagorean theorem. All right, flip your paper over or go to your second page. Here we go. Let's talk about a couple of operations. And we're going to go through these pretty quick because they're simple and you're going to think they're simple. All right. First one, if we are adding or subtracting, this says we're going to add or subtract their corresponding parts. All right. Could you write down vector U and vector V? And we will use the same ones when we talk about scalar. All right, vector U is 3i minus 2j, and vector V is -2i plus 5j. So if I want to do U plus V, it's as simple as it looks. You're going to add the two vectors together. 3i minus 2j plus -2i plus 5j. Here, the I and the J don't act any different than a variable when we combine anything. We just add them. So my I's give me 1, so 1i or just I, and my J's give me 3, so 3j. There's no catch, that's it. All right, so then we have scalar you're looking at. So scalar multiplication, you just multiply. So here's an example. If I want to do -3u. I'm just going to do -3 times 3i minus 2j. I'm going to get -9i plus, because I'm careful with my signs, 6j. All right, none of that was crazy, right? That acts normal. So this is to show you that the math that we do with them is normal. They behave normally when you want to combine them. So then let's look at that third thing you have, which is what a resultant vector is. So let's talk about a resultant. Here's what it says. A resultant vector is the geometric sum of two vectors extending from the initial point of the first vector to the final point of the second. So what is this? What's this trying to say, right? This is trying to say what happens when two vectors, when two forces act on the same object. Okay, that's what we're trying to show here. So let's take U and V. I'm going to shift them around a little bit. And I'm going to put them here. And I'm going to say, hey, this is an object. All right, so here is a tug of war that I'm having with my neighbor's dog. Her name's Leota, if you were wondering. She's a black lab. She's beautiful. All right, so Leota and I are tugging on this rope, right? That is the blue dot, okay? Now I'm pulling in the U direction. I am vector U is me, okay? I'm pulling it. Now that vector is longer because I'm stronger than that dog. She's a puppy. I don't know when she's full size if I'll be stronger or not. I hope so, but debatable, all right? So I am vector U, and the length of that vector is how hard I'm pulling, okay? Now Leota is the blue vector. So she's the blue vector, and it's shorter because she's not pulling as hard. And we're pulling in different directions, right? So when you find a resultant, what you're finding is where would that object, what's the force actually happening on that rope that we're tugging on, okay? So here's the combined force is the resultant. And what it says is that you put them from the initial point of the first to the final point of the second. Here's what that means. Really, when I want to see how those two are acting together, I want to put them end to end. To see how they act together, you put them end to end. And you connect. So that pink line, that is the result. And that is the geometric sum of U plus V. What actually happens as we're pulling on them. That's the force, because it should make sense, right? If we're both pulling, we're pulling both up. I'm pulling to the left, she's pulling to the right. So that object is getting pulled definitely up and stronger because we're combining. And then what direction is it going in? It's leaning a little bit towards me because I'm pulling harder, right? So that's the idea of the resultant, the geometric sum. That's what's happening. So a lot of times we'll see two vectors acting on the same object, two tugboats pulling something in between them. And you want to see, well, how do their forces act together on that object? That's what we're looking at a lot of the time. All right. So here we go. Next thing, we are so close. We got this. You guys are doing a great job hanging on. So let's bring it together so that we can write these and we can see how trig fits in, because we haven't actually used trig yet with a vector, right? So that's going to happen here. So this says, let's relate magnitude and direction to our AI and BJ. All right, so I have a picture over there of my vector. All right, so that is my vector V. All right, it's going there. It goes to some point A, B. So we know that our X distance, I in this case, is A, and then the B is our J component. And we know, because we're talking about X and Y, we know that makes a right triangle. All right, so just like in trig, there's our theta, we have an angle. So now we can get some relationships going. Here they come. Sir Sixer-Tix, you ready? Sine of theta. Sine of theta is the y over the r. My y here is b. My r is the magnitude of the vector. That's just sir. It just looks funny. And cosine, Sixer, cosine of theta is the x over the r. So my A over the magnitude of my vector. And what am I trying to do? I'm trying to take my vector v, that is ai plus bj, and I'm trying to relate it to the magnitude and the direction, what vector talked about, right? A vector is magnitude and direction. So how do I take just the over and up and turn them into magnitude and direction? This should feel like polar, I think. If sine of theta is b over magnitude of v, I'm going to multiply that v over. Okay, I'm going to multiply that over, and I'm going to say then that v is the magnitude of v times sine of theta. Okay, I multiplied it over, just rearranged. I'm going to do the same thing in my cosine equation. I'm going to take that v, I'm going to multiply it over. What do I get? I get that a is magnitude of v times cosine of theta. Oh man, that looks exciting. This, y is r sine theta, x is r cosine theta. Can you see it's the same thing? It has different letters and that's funky, but it's saying the same thing. It's still Sir and Sixter rearranged using our triangle. So what that says is if I have a vector, instead of calling it ai plus bj, I could also call it, or instead I could call it the magnitude of v times cosine of theta. That's my I. Plus magnitude of v sine of theta is my j. I just substituted in what we solved for. All right, that formula is something we're going to use a lot while we do vectors. Okay, so mentally prepare. If you want to circle it, star it. This is like the big idea, what I was trying to make sure we got through. And I just want to show you one problem where we take magnitude and direction and write it as a vector. This is what we need to be able to do. We need to be able to write a vector in terms of its components and in terms of the angle and the magnitude, because that'll allow us to write vectors that describe force and describe direction so that we can actually use this. All right. So to tie that together, let's do this last problem that you already have on your paper. It says, write a vector in terms of I and j, given this, that the magnitude of the vector is 8 and that the angle theta is 30 degrees. All right, so we're just trying to write the vector. That's all we're trying to do. So our formula says this, my vector v is, I'm going to write out the formula. You can choose whether or not you're willing to do that again. I think you could be. All right, that's our formula, right? Magnitude of the vector times cosine of the angle is my I. Magnitude of the vector times sine of the angle is my j. So 8 cosine of 30 is my I, plus 8 sine of 30 is my j. Can I solve this? You bet I can. Cosine of 30. Anybody know it off the top of their head? Root 3 over 2. Love it. Sine of 30 is a half. All right, so what does this vector look like? This vector looks like 4 root 3 I plus 4 j. Now, I wanted to do that using the formula for the vector, right? But you could also do it by drawing. And you could say, hey, this is 30. There's my 30 degrees, okay? Here is the magnitude, which is 8. If you know 30 degrees and your hypotenuse is 8, can you find these two sides using trig functions? You better be able to, right? I should certainly hope so. So can you find, the AI and the BJ that you're looking for without having to write this formula? I think you can. And if you're more comfortable doing that, do it. Draw a picture. Say, okay, I have my angle, I have my hypotenuse. Cosine. The x, I don't know, over the r. Let me solve that. Sine. The y over the r. Let me solve that and put it back in. Formulas are supposed to just be shortcuts, right? When you're given a formula, it's saying, hey, I have it all written out so that you don't have to think through solving Sir-Six or Tix every time. But if it's a hindrance because it looks funky, then do it normally and say, hey, I'm going to break it apart to sine and cosine. I'm going to find those two sides, right? That is the background that I wanted you to have, okay? Next class, we will start applying this. I promise you made it through. That was a lot to get through. You did a really nice job. So what I'm going to ask is this. You have an assignment, right? So you're going to have an assignment that's just what we did in class. It's just basics of vectors. It's in Pearson. I don't think it should take you very long. Make sure you submit your work. And then don't forget about your project being due Friday, all right? In class on Friday, we will really hit the applications, which I'm pretty excited about.